Okay, I'm gonna start over. So CompiledLayer is a system symbol that was introduced in 12.2 that basically unlocks the ability to create a neural network layer whose computation is defined by the user via a function object that gets compiled by the compiler. So it's an intersection between the compiler and the neural network framework. So yeah, at its basic level, it takes one argument, which is a function object that is suitable for compilation. So it has to have all the typed annotations required by the compiler. And so it supports packed arrays, numeric arrays as containers, and pretty much all the precisions except for data types, sorry, except for like complex numbers. Okay, so it is a normal neural network layers, so it's integrated with the framework and it can be freely used in whatever you want to do with the framework. So for example, here, it can be used in a larger network. So this is the compiled layer, and for example, it can be trained. So I'm creating some fake data and training this network, which uses the compiled layer. So it's implemented via it's implemented via MXNet because that is the backend that the entire framework uses. And in particular, basically every layer in the framework gets translated to one or more MXNet operators in the evaluation pipeline. And the operator that backs compiled layer is this MXNet backtick custom. So this is the name of the custom operator in MXNet. This is a way, like once you have loaded the neural network framework, you can check. Basically, these are all the operators that are available in MXNet. So there are a lot. And this is what backs compiled layer. So it takes an op type parameter, which basically corresponds to the function that defines the layer, and it has to be registered before it can be used. So its op type parameter must be set to a previous register operator. The operators are registered using the MXNet C API. We do it in MXNet Link. And they require a lot of things, but the most important things that custom operator registration requires is a function pointer that defines like what the layer should do. And this function pointer is obviously a pointer to the compiled function that's provided by the compiler. So you can extract the pointer by taking the fourth argument of the compiled function expression. So we pass this integer, which is interpreted as a memory address, and so MXNet knows where it has to look for to run the specific instance of custom operator we have requested and registered. Okay, so let's look at gradients and automatic differentiation. So this is an important feature of compiled layer. So as with every neural network layer, you must be able to compute gradients. That's a crucial part, and compiled layer can obviously do that. Now let's wait a few seconds for this to compile. Compilation is still a bit slow, but in compiled layer, I can mention we have a caching mechanism, and so if you run this code twice, it's very fast because it doesn't recompile. We cache the result of the compilation. Okay, so this is a simple function which computes sine plus cosine, and we can just run the layer on an input, just like a function, and it's computing sine plus cosine. But we can also compute the gradient, the derivative. And the way we do that is by passing this property here. And in this case, this will compute the derivative of this function. So how does it do that? It uses a separate compiled function to compute the gradient, which we call gradient function. So you can either click on the plus sign here, you will see two parameters. Layer function is the function that we have passed, which defines the so-called forward computation. And the gradient function is what computes the gradients, which in this case is automatic. And I'm going to explain what this is. And besides looking at the panel, you can also programmatically access net extract. We can extract these two properties. This is the layer function, and this is the automatic for the gradient function. Okay, so in the default case, when we don't pass anything else, the gradient function is going to be automatic, and it's going to be provided by the automatic differentiation framework. This doesn't always work. When it fails, you still get a layer out, but it's a layer that it's unable to compute gradients. So here, this is a function that auto differentiation cannot auto differentiate. And first, you get the error from the attempt to compile the auto differentiated function. We let it pass because it might give useful information about the compilation failure to the user. And then you get the proper compiled layer error, which says that automatic differentiation failed, and you cannot use the layer to training or to compute gradients. So in this case, you get none here, as you get here. And so if you try to either train or compute a gradient, you get an error message saying that there is one or more compiled layer which have a missing gradient function, so this cannot be done. Also, the gradient function can be manually disabled. If you want, you can pass none, and you get the same thing as this. Okay, so the other option when automatic differentiation fails is that the user can manually provide a gradient function. So here, now I'm going to use the forward and backward terminology. So this is the gradient function, and this is the layer function. Now this is not actually the gradient function for this. This is just a random thing. It's obviously up to the user to do the correct thing here. But yeah, you can pass a function object here, and in this case we just try to compile it and do not use auto differentiation, and you will see the gradient function spelled out here in this case, and we can compute gradients again. Now let's look a little bit closer at the relationship between this and this, like what this function should actually do, because it doesn't just compute the derivative. First of all, it takes two arguments. So yeah, let's discuss this. So I'm gonna use this picture. Let me make this a little bit larger, maybe. Okay. So yeah, I'm gonna use the forward and backward terminology. So the forward pass is where you apply the layer function. So it's a normal layer evaluation, and it's very simple. You take an input and you apply the function f, and you get an output back. So here, like this input is a vector. It has an index I. This output has an index j. But you can also have like n-dimensional arrays. You can just flatten them into a vector, and everything I'm going to say still holds. Yeah, these are two different indices representing that this input and output can obviously have different dimensionality. They don't have to be the same size. So this is the forward. The backward pass is what uses the gradient function. And first of all, it takes two arguments. You can look at this picture in the bottom part. It can take three arguments. So this dashed line means that this argument is optional, is not like mathematically required. So we're gonna focus on these other two for the moment. So it takes the same input to the layer function, and then it takes another vector, which we call the outgrad. So the outgrad has the same dimensionality of the output, but it's not the output. And what it computes is this. So this is the actual derivative of the f function. This is the Jacobian matrix. the derivative of the output with respect to the input. And then it makes a dot product or tensor contraction, however you want to call it, with this outgrad vector. So there is a sum over j here. This entire object has an index I. We call the result, we call it ingrad. And so this has the same dimensionality of the input. So it's this guy here. Okay, so who are these ingrad and outgrad? Well, they are the arrays that take part in the back propagation algorithm. So I'm not gonna spend much time discussing this, but this is basic like neural network stuff. So you gotta imagine there is, like, for example, 3 layers. They don't have to be 3 compiled layers. They can be whatever. Okay. So imagine this is the first layer. This is the last layer. We are computing gradients, and the main scenario in which you want to compute gradients is training. And during training, the last layer is usually the loss function. So imagine that this output here provides the value of the loss function that we want to minimize. So obviously, inputs and outputs this is a chain. So like the output of the first layer becomes the input to the second, and so on. And the same happens for outgrad and ingrad. So the ingrad produced by this function becomes the outgrad produced by this. Now, the endpoints are obviously here and here. So this input here is the externally provided data, while this outgrad provided here is a vector of ones. So if the layer is the last one, you feed a vector of ones as the outgrad. Then apply. So first you make a forward function, a forward pass. So set the input, propagate everything down to here. Then you set the outgrad, run the gradient function for the loss function, get your ingrad, and you keep going backwards. So I'm not gonna prove this, but under this picture, what you get in these ingrad arrays are the derivatives of the loss function with respect to the corresponding input. So for example, this array will contain the derivative of the loss function with respect to this input, while this array contains the derivative of the loss function with respect to this, and so on and so forth. And this is exactly what you want when you train a network, because you want to get the derivative of the loss function with respect to your learnable arrays in the network that you want to optimize. But the learnable arrays are just a subset of the inputs to all the layers. So yeah, this is how it works. So the gradient function, yeah, so it can take 2 or 3 inputs. So the third argument is optional, and it's the pre-computed output that is provided by this. So we have left the ability to provide a function that takes 3 arguments, because this third argument can be useful. It's an optimization. It's the possibility of an optimization, because sometimes you just compute the ingrad faster if you have access to this. So it might be useful to save time. And a typical example is a product reduction operator. So suppose our input is a 4-dimensional, like vector of length 4 for simplicity, and our forward function just multiplies all the elements together. So in this picture, well, I should maybe do, let's say, it does this so that we don't have scalars, but it's the same, it doesn't matter. So in this case, the outgrad is a single number because it has to have the same dimensionality of the output, which is a vector with 1 element. And if you apply this formula, you basically get a product between, so the Jacobian matrix becomes a vector and the outgrad is a single number, so you get this. And the elements of this Jacobian matrix are the derivative of the product with respect to every single scalar in here. And so it's basically, I've explicitated, but it's basically you take out the corresponding element from the product. So in this case, let's see. Yeah, you can recast this as this operation where you have the product of all the numbers divided by each one of the entries. And so you can identify the pre-computed output. And this representation is faster to compute because here you have to compute 3 times 4, you have 12 multiplications, where here you have to do 4 divisions. And in general, it's n divisions versus n times n minus 1 multiplications. So this is something that scales better to compute the INGRAD for this kind of operator. Obviously, this only works when none of these guys are 0, but in that case, you can fall back. And actually, yeah, there is actually an MXNet bug. There is an operator in MXNet which does this operation, and it has a bug that where one of the elements are 0 because it's using this. Anyway. Okay, so from this entire picture, it follows that there must be tight constraints between the arguments of this function and the arguments of this function. So for example, the first argument is always the input, so it has to be coherent. They have to take an array which is the same type of container with the same rank and the same data type. But also the outgrad and the output must have the same, they must have the same signature, so to speak. So container, data type, and rank. And so here, as an example, I am violating one of such constraints because the forward function takes an array of rank 1, so list, and it returns a matrix. But the backward function, in its outgrad, it takes a list. So this is rank 1, this is rank 2. And so, yeah, in this case, you get an error saying that the second input of the gradient propagating function, so this guy must have the same signature as this output, and it doesn't. So you have to be coherent, obviously. Okay. Now, yeah, let's discuss another interesting part, which is shapes and what happens with the batch dimension. So, our neural network framework is mostly a static framework, which means that if you want to run a network on an input, all the input and output dimensions of all the layer in the network, they have to be set before the network can run. If they are not set, we silently attempt to set it under the hood by using the shape of the data, which is why all the previous example worked, because like here in this compiled layer, you can see in this panel that input just says array. This is supposed to have like a well-defined shape, but it's still working because we're feeding a vector size 3. But like under the hood, everything has to be specified, and sometimes this cannot be inferred. So here I'm gonna make all these settings explicit. So yeah, in this case, this is a network with some layers and no shape specifications. So these here it doesn't show any well-defined shape. There are still like a little bit of knowledge that you can use, given that we're using some layers which we know that they cannot take any general array, but still these are not well-defined shapes. So the way you specify shapes is either you set the input option to the first layer, or you set the input option to the net chain container, which is the same thing. And in both cases, here now everything is specified and this network is ready to run. Well, this has to be initialized because these are learnable arrays, but that's a different story. Okay, so CompiledLayer accepts an input shape specification just like any other layer. So here I'm going to make this explicit, and here we'll see that input and output, it says size 3. Now, how does this know what the output shape is? Well, we just run this function on a sample input internally. So when the user specifies this, we have a function, we have the input, we compile the function, and we just run it on some synthesized data to see what the output shape is. So this, in this case, this is an element-wise operation, so it's obviously giving the same shape. This is a more non-trivial case, so this does something less trivial. Input shape is this, and what we do is we just generate a sample input with this shape. We run the function on the input, and we get the dimensions, and we put it here. So this can obviously create problems because the framework is static, but the compiled function is not, because it only wants a rank, not a well-defined shape. So one thing that can happen, well, if you just change the input shape here, we will just play this game again and update the panel. That's no problem. A problem can happen when the function doesn't always return an array of the same dimensions when the input dimensions are fixed. So, for example, imagine a weird case like this. If the total, if the total of the input is below 10, I will just return the input. Otherwise, I will just concatenate the input with itself. So this is a case in which the output dimensions of the compiled function depend on the data. And this is bad for CompiledLayer. So what happens in this case is that during the shape inference, we will do this sample evaluation, and we will go into one of these two branches. In particular, we go in this branch for this case. So the panel, it says that the output shape is size 3. Now, at runtime, we check that the output has the same shape as what you expect it to be. So in this case, it's fine because the total is below 10. But if we feed this, you get an error here because the shape was unexpected. Please ensure that the shape of the arrays only depends on the function input shape and not their values. So this is something that one must be mindful of. Now, about the batch dimension. So in MXNet, which is the library that we use in the backend to run all these computations, nets operate on arrays that have one extra dimension with respect to what you see in these panels and like in these panels, for instance. So this is called the batch dimension. And this is what allows us to natively support listability in the framework. What happened here? Layer. Okay, maybe there was some input cell missing here. Anyway, let's try this. And this, okay. So everything is natively listable, and like we're not doing this by mapping the layer over the inputs. We're actually in MXNet, we're actually running everything on these larger inputs, and we just scale the size of the batch dimension. And in this case, what we're actually doing is this. Okay, so now there is a input shape specification here, but there is also a rank specification here for CompiledLayer in the function that we're going to compile. And these two informations, they have to be coherent. So when you feed, like what you feed here has to be coherent with the signature of the input here. Now, there are two cases that we support. One is one might normally expect is the case in which the rank of the function is the same as the rank of the layer. So rank 1 and input is a list, is a one-dimensional array. In this case, the compiled function acts on objects that have the same dimensionality as what appears in the layer panel here, which means that in MXNet, they will actually be mapped over the batch dimension in this case. So here, I am defining a function, building a compile layer out of the function, but I'm also compiling the function explicitly manually. And I'm going to show what happens for when we run the layer on input. So in this case, when we run it on a single vector size 3, what actually happens is we wrap the input on an additional list because everything has to be one extra dimension of XNet. We map the compiled function over it, and then we take the first. If we feed a batch, we don't have to wrap an extra dimension because this is already a batch, but the CCF, the compile function, still has to be mapped. Like we don't map the entire network over the batch dimension, but if the network contains a compiled layer and the compiled layer has the input rank of the function equals to the input rank of the layer, then that function is actually mapped. The second case is where the function rank is equal to the layer rank plus 1. So this means that the compiled function is already acting on batches. So for example, this is rank 2 again. This is list of size 3, but this takes rank 2. And this is still accepted by CompiledLayer. And in this case, what happens is that the CCF is not mapped over the inputs. So in the so-called unbatched case, where there is one example only, we wrap it into a list. We add an extra dimension and run the compile function. And if the input is already a batch, we just run the compile function. Okay. So this case is supported because it must be useful for various reasons. One is that the mapping of the compile function that we do in case 1, for the moment, is done serially. It's not parallelized. While in case 2, you might natively write a function that employs vectorized operation or parallelization. Like I think this case is already doing that. Like I think if you run the sign on an n-dimensional array with any elements, I'm pretty sure it's not computing it serially, but it's parallelizing the computation. The second reason is that in this case, the CCF, the compile function, sees the entire batch. And so it can make different batch elements interact with each other, which is something that you cannot typically do with other layers in the framework, except for one layer, which is batch normalization layer, which is defined to act on batches and does some very specific operation. But here you can implement arbitrary batch-wise operations if you want, in principle. So all other cases, they throw an error. So for example, here I have rank 2 and rank 3, and this is complaining because these two things are not coherent. Okay, so this is the end. Yeah, this was short. I was expecting around 30 minutes, which is exactly how it went. So now, for the future, the main thing that CompiledLayer needs is to support multiple inputs. Until it does that, it's like its usefulness is quite limited, honestly. And the main reason is because supporting multiple inputs means that it can support learnable arrays. Right now, with one input, you cannot have a learnable array inside the layer. A learnable array means you need an extra input. So this layer is not learnable, which limits the amount of operations you can do. While if the layer supports learnable arrays, you can start doing stuff like weird modified convolutions that people used to use in research, or like other things. So this is the main extension. We have kind of like not given CompiledLayer so much attention in the latest years, but this is changing now because we are starting collaborating way more closely with the compiler team. For now, we are focused on some internal restructuring and so not in like things that you can see from the user perspective. Like we have improved our auto differentiation pipeline. We try to compile the forward and backward function in the same compiler code to save time. And the current endeavor is with this batching business. When you have case 1, so when you have the function rank, that is the same to the layer rank, instead of mapping the function manually in C, we will get a function that natively works on the batches from the compiler. So before we compile, we just compile the function, and then we map the function over the batch in C, while what it will look like after the current project is merged is that we compile map of F, basically. And this allows us to avoid like branching our downstream pipeline for evaluation in MXNet. So I hope after this is done, we can start to tackle the big feature here, multiple inputs. So yeah, that was it.
Just thank you, Matteo. That's really nice. I had one question. Can you have trainable parameters in these layers?
Can you have what? Sorry.
Trainable parameters. So can you have?
Yeah, not currently.
Okay.
But so it's the multiple input support that I was discussing. It needs, like, having trainable parameter is this exactly the same thing as having additional input in the operator, because the operator has to use, the data input and the trainable parameter to do stuff, which means it has to accept more than one array. So multiple inputs means that we will be able to create a layer which has 2 data inputs. So you will see, like in the net graph panel or in the layer panel, you can take 2 inputs. But it also means that you will be able to have 1 input and 1 learnable array, or 1 input and n learnable arrays, or any combination of the 2.
I see. Okay, thank you.
There are no more questions, I guess.
Probably not. Thank you, Matteo.
Thank you, Matteo.
Thank you. Bye.
Okay. Bye-bye, everybody.